Hello friends, it's Kalpesh Jani and I'm very glad to address you people via this medium of video presentation. So let us now proceed friends to derive the Maxwell relations in thermodynamics. But before doing that, let me first introduce you with a mathematical theorem which is known as the Schwarz theorem. Now this theorem is very useful in obtaining the Maxwell relation in thermodynamics. Now let us have the brief introduction of this theorem. Suppose you have a function a which is a function of two variables x and y. This is a continuous analytical function. Now suppose you take the first order differentiation of this function with respect to x while keeping y constant. So you will get this term on left, which is the first order differentiation of a with respect to x when you have kept y constant. In the same manner, you can also have first order differentiation of a with respect to y while keeping x constant. So you get these two first order differentiation of this function with respect to each of the variables. Now you proceed to obtain the second order differentiation. So on the term on the left side, if you proceed to get the second order differentiation, you will get this term where you differentiate further this left side term with respect to y while keeping x constant. So this the term on the left side at the bottom of the slide shows the second order differentiation of a with respect first to x and then with respect to y. In the same manner, the term on the right also can be differentiated for the second order differentiation with respect to x while keeping y constant, and you get this term. So the two terms on the bottom of the slide are the second order differentiation of the function a with respect to x and y. First we have differentiated with respect to first x and then y, and on the right we have differentiated a with respect to first y and then x. And the Schwarz theorem states that these two second order differentiation are exactly equal. So this is what the Schwarz theorem is all about. So the second order differentiation is irrespective of the sequence of the variable that we use. Uh, that doesn't mean that the first order differentiation of these two with respect to different variable is they are equal. These two terms are not equal. This term and this term are not equal. But the second order differentiation are always equal. So this is what the Schwarz theorem is all about. So let us make use of this theorem for the thermodynamic potentials. We know that all our thermodynamic potentials are dependent on some natural variables. Now, and each of these thermodynamic potentials have two natural variables. So we can apply this Schwarz theorem for the thermodynamic potential. This is what the Maxwell did. He applied this theorem to the thermodynamic potentials, and when we do so, we get very interesting interrelation of the thermodynamic potential and the thermodynamic potential with the thermodynamic entities, and they actually have a very useful information which is possessed uh, by them. So let us go uh, towards the derivation of the Maxwell's relation. So we shall start with the Maxwell's first relation. We know from the first law of the thermodynamics that dq is equal to du plus dw, where du is the change in the internal energy of the given system, dw is the amount of work that is done by the system, and dq is the amount of heat that is supplied to the system. Now, if the system, as I have told you, that if the system is an isolated system and the process we are right now concerning is a reversible process, then we can show that this change in the internal energy is nothing but TdS minus PdV. It can be shown by this equation. du is equal to TdS minus PdV. Now, this U is the internal energy potential, thermodynamic potential of the given system, and this equation shows that this internal energy potential of the given system is having is dependent on two natural variables. Here it is, they are entropy and volume. So U, internal energy of the given system, is dependent on entropy and volume. So now we can apply Schwarz theorem to this thermodynamic potential, and let us take the two successive second order partial differentiation with respect to each of these variables, and then equalize these two second order partial differentiations. So we shall have to take the two second order partial differentiation. On the left side, we shall first take the partial differentiation of u with respect to s while keeping v constant, and then we shall differentiate it further with respect to v while keeping entropy constant. So that makes the second order differentiation of this function, which is on the left side term. In the same manner, you can do the same thing in the reverse order of the variables. First you differentiate u with respect to v, and then you differentiate further with respect to s. So according to the Schwarz theorem, these two second order differentiations should be equal to each other. So now let us make use of this Schwarz theorem and work out the Maxwell's relation. So let us start with the term du is equal to TdS minus PdV. We have to take the second order differentiation, partial differentiation of internal energy U with respect to S and V. Consequently, in one case, we shall first differentiate with respect to S, and in the first differentiation, first order differentiation, then after we shall differentiate with respect to V. And in the second case, first we shall differentiate u with respect to v, and then after we shall differentiate with respect to s. So we get two second order differential term of this function, thermodynamic potential function u, and then we shall equate these two second order differential term according to the Schwarz theorem. So let us first take the first order differentiation of u with respect to s and v. So on the left side, it is shown that if you take first order differentiation of u with respect to entropy S at a constant volume, it is nothing but T. And on the right side, you can see that if you take first order differentiation of u with respect to volume V at a constant entropy, it is nothing but minus P. So we have taken first order partial differentiation of internal energy u with respect to S, and in the second case we have taken the first order partial differentiation of u with respect to v. Now further we shall differentiate these two terms with the next variable. We shall take the second order partial differentiation of these two terms with the next variable. So if you do so, then we have to differentiate del u by del s further with respect to v with keeping entropy constant, and when you do so, we have also to partially differentiate T with respect to V. So we get del T by del V at a constant entropy S. In the same manner, on the right side, we can further partially differentiate del U by del V with respect to S. So we get del U by del V, which is further differentiated with respect to S as a constant volume, and if you do so, we have to take the partial differentiation of P with respect to S also. So we have to have a minus del P by del S as constant V. So these are two second order differential terms, and according to the Schwarz theorem, these two terms must be equal to each other. So the equation that we have derived on the right side of these two terms are also equal. So these are nothing but the first Maxwell relation. Del T by del V at a constant entropy S is nothing but equal to minus del P by del S at a constant volume V. So now let us take the second relation, Maxwell's relation for thermodynamics. Here we shall start with Helmholtz free energy, which is given by this equation, F is equal to U minus ds. So if you take the differentiation of this F, you get this equation, dF is equal to derivation of U minus ts, which is nothing but du minus tds plus s dt. Now you know the value of du from the uh, very first Maxwell relation, that du is nothing but TdS minus PdV. So putting this value in the equation of dF, we have the value of dF is equal to minus PdV minus SdT. So we have got the uh, equation which shows the change in the Helmholtz free energy, derivative of the Helmholtz free energy, which depends upon volume and temperature. Volume and temperature are the two natural variables of the Helmholtz free energy. So let us now take Schwarz's theorem for this thermodynamic potential, and we can say that the second order differential equation of Helmholtz free energy with respect to V and S, V and T, I'm sorry, should be equal. So we have to take these two second order derivative term of F. So let us start doing that. We know that dF is equal to minus PdV minus SdT, as we have seen in the previous slide, and we have to take this second order differentiation of F. Now let us proceed first to take the first order differentiation of F with respect to T and V. So if we take first order differentiation of F with respect to T, del F by del T at constant V is nothing but minus S, as can be seen. And if you take the first order differentiation of F with respect to V at constant T is equal to minus P, as can be seen from the equation. Now we shall further go to obtain the second order differentiation of these two terms. So on the left side, we further differentiate del F by del T with respect to V. So we have to differentiate S with respect to V also. So we get minus del S by del V at a constant T. In the same manner, on the right side, we further differentiate del F by del V with respect to T. So we have to differentiate minus P with respect to T also. So we get minus del P by del T with respect to with a constant V. And according to the Schwarz's theorem, we can equate these two second order differential term. So we have the equation del S by del V at a constant T is equal to del P by del T at a constant V. So this is nothing but the second Maxwell's relation for the thermodynamics. So let us take Maxwell's third relation. Here we shall start with the enthalpy H, which is defined as H is equal to U plus PV. Now we shall differentiate this. We get dH is equal to differentiation of U plus PV, which is nothing but du plus PdV plus VdP. Now we shall put the value of du as TdS minus PdV, as we did in the previous relation also, and we get the value of dH is equal to TdS plus VdP. So here we can come to know that this enthalpy is the function of two natural variables, entropy and pressure. So we can show that the second order differential of this enthalpy with respect to entropy and pressure must be equal according to the Schwarz's theorem. So we shall proceed to do that. So we shall proceed to obtain this second order differentiation two terms for the thermodynamic potential of enthalpy. So we shall start with the equation dH is equal to TdS plus VdP, and then we shall take the second order differentiation of this enthalpy H with respect to entropy and pressure consequently, and we have to equate these two second order differentiation terms. So let us first proceed to have the first order partial differentiation of this function H with respect to each of the variable. First we shall take the del H by del S with at the constant P, which is nothing but capital T, as you can see in the slide, and we can also take the first order partial differentiation of H with respect to P, which is nothing but del H by del P at a constant S, which is nothing but V. Now we shall further differentiate these two equations with the next variable. So we take the second order partial differentiation of these two terms. So on the left side we get we differentiate del H by del S further with respect to P at constant entropy. So we have to differentiate T also with respect to pressure P. So we get del T by del P as a constant entropy S. On the right side, we further differentiate del H by del P with respect to entropy S at a constant P. So we have to differentiate V also uh, with respect to S. So we get del V by del S at a constant P. Now, as we know that from the Schwarz theorem, these two second order differentiation should be equal. So we get this equation del T by del P at a constant entropy S is equal to del V by del S at a constant pressure P, which is nothing but the third Maxwell relation for the thermodynamics. And so now let us proceed to derive the fourth and the final Maxwell relation for the thermodynamics. We shall start here with Gibbs free energy, which is defined as G is equal to H minus Ts. We shall take the differentiation of this and you get dG is equal to the derivative of H minus Ts, which is nothing but dH minus Tds plus SDT. Now here we have to put the value of dH that we have already derived in the previous slide. We have to put the value of dH, which is nothing but TdS plus VdP. So if you put the value of dH, you get the value of dG as dG is equal to VdP minus SdT. And so we then after proceed to take the uh, second order differentiation of G. Now as you can see from the equation itself that G is the function of pressure and temperature. So there are two natural variables with which the Gibbs free energy can be differentiated. So we take second order differentiation of G with respect to pressure and temperature. So let us proceed to do that. So here we have the equation dG is equal to VdP minus S dt. G is a function of pressure and temperature, and we have to take the second order differentiation, partial differentiation of G with respect to P and S. So P and T, and so we have to take these two second order differentiations and then we have to equate them. So let us first take the first order differentiation of G. First we shall differentiate G with respect to P while keeping T constant, which is nothing but capital V, and on the right side we differentiate G with respect to T, del G by del T at a constant pressure, which is nothing but minus S. So we shall further proceed to take second order differentiation of these two equations with respect to the next variable. On the left side we take the second order differentiation of del G by del P with respect to T again at a constant pressure, then that will give the partial differentiation of V with respect to T. So we get del V by del T at a constant pressure. In the same manner, on the right side, we take further differentiation of d del G by del T with respect to P at a constant temperature, and for in the same manner we have to take the differentiation of S with respect to P at a constant temperature, so it gives minus del S by del P at a constant temperature. And as we know from the Schwarz theorem that these two second order differentiations should be equal to each other, so we can equate the terms on the right side of both the second order differential equations. So del V by del T at a constant P is nothing but minus del S by del P at a constant T, which is nothing but the fourth Maxwell's relation. Okay, so now in this slide, let us summarize all the outcomes that we have so far derived in terms of the four Maxwell relations. From the first Maxwell relation, the outcome that we have derived are shown in the slide. On the left side are the interrelation of the thermodynamic entities as the derivative of the other thermodynamic entities, like del T by del V as constant entropy is nothing but minus del P by del S as constant pressure P. And on the right side, how can we show the thermodynamic entity as a derivative of the thermodynamic potential? Here temperature can be shown as the derivative of internal energy with respect to entropy at a constant volume. In the same manner, the pressure can be shown as the negative derivative of internal energy with respect to volume at a constant entropy. So this is the outcome of the first Maxwell relation. The second Maxwell relation tells us, it gives the interrelation between the thermodynamic entities, the in the way that is shown in the slide. Del S by del V at constant T is nothing but del P by del T at a constant V. And on the right side we can define the entropy and pressure as the negative derivative of Helmholtz free energy with respect to temperature and with respect to volume. So entropy can be defined as the negative derivative of Helmholtz free energy with respect to temperature at constant volume, and in the same manner pressure can also be defined as the negative derivative of the Helmholtz free energy with respect to volume at constant temperature. So this is the outcome of the second Maxwell relation. From the third Maxwell relation we came to know the relation between Tp, V and S in this manner. Del T by del P at a constant entropy S is nothing but del V by del S at a constant pressure P. And on the right side we can define temperature as the derivative of enthalpy with respect to entropy at a constant pressure, and volume as the derivative of enthalpy at an enthalpy of with respect to pressure at a constant entropy. So this is the outcome of the third Maxwell relation, and the outcome of the fourth Maxwell relation can be given like this. Del V by del T at a constant P is nothing but the negative derivation of negative differentiation of del S by del P at a constant T. And on the right side we can show the volume and entropy as the derivative of Gibbs free energy with respect to pressure and temperature. So volume is nothing but the derivative of Gibbs free energy with respect to pressure at a constant temperature, and entropy can be shown as the negative derivative of Gibbs free energy with respect to temperature at constant pressure. So all these four Maxwell relations give us the interrelation between the thermodynamic entities, and we can also define the thermodynamic entities as the derivative of the thermodynamic potential. So these are all the outcome of the Maxwell's equation, which are very useful in many situations. You can predict many things from these outcomes. Now let us first because on the right side you can see that temperature can also be defined as the derivative of internal energy with respect to entropy at a constant volume, and temperature can also be defined as the derivative of enthalpy with respect to entropy at constant pressure. So temperature can be defined by these two ways. So each of these thermodynamic entities can be defined in more than one way with the derivative of the thermodynamic potential. So let us just find out in how many ways all these thermodynamic entities can be defined as the derivative of the thermodynamic potential in the next slide. So as you can see here, there are this many relations which can be shown for the thermodynamic entities, which can be shown by as a derivative of the thermodynamic potentials. Now let us first sort it out it a little bit. So okay, now we have sorted them out. So we have the temperature which can be defined by two ways, the pressure which can also be defined in two ways, volume can also be defined in two ways, and entropy which can also be defined in two ways. So temperature, finally we can show the temperature as the derivative of two types of the thermodynamic potentials, or each of the thermodynamic entities can be shown as the derivative of two types of the potentials. So let us see in the next and the final slide how can these thermodynamic entities be given as a derivative of different thermodynamic potentials. Okay, so in this final slide, we can see that temperature can be seen by these two derivatives. It can also be seen by it can also be seen as the derivative of internal energy with respect to entropy at a constant volume, and also as the derivative of enthalpy with respect to entropy at constant pressure. So each of these thermodynamic entity can be shown as the derivative of the thermodynamic potentials. So these are all the outcomes which are very useful in many calculations, in many situations. So I hope that you have gone through all these Maxwell relations and you find this video, you have found this video very useful to you. So thank you for watching.